Hi there, my name is Zhi-Qi. I'm a postdoctoral research associate at Carnegie Mellon University. I'm excited to present our work, Rethinking Spatial Invariance of Convolutional Networks for Object Counting. Previous work generally believes that improving the spatial invariance of CNN is a key to object counting. Based on this data point, more and more networks such as multi-column and deformable CNNs are studied for object counting. However, this research direction has appeared to be performance bottleneck. Some recent studies witnessed a lot of noises during the density map generation and suspect that this might be the reason for the performance bottleneck. Although these efforts have made some progress, we are still unknown of the following question. First, how does density noises affect the performance? Second, is only improving the spatial invariance valuable for object counting tasks? Before answering this question, let's briefly introduce the density map generation process. Here, we take crowd counting as an example. The density map is generated by smoothing the central point with multiple Gaussian kernels. In general, there are two types of noise. First is the error between the actual point and the annotation. The second is the overlay of multiple Gaussian kernels. More details of the analysis are in our research paper. To answer the previous question, we have thoroughly verified four mainstream object counting methods. Extensive experiments reveal that too strict pixel-level spatial invariance will not only cause large prediction variance, but also overfit the noises in the density map. In general, this experiment shows the following answer. First, only increasing the spatial invariance is not beneficial to object counting tasks. Second, the pixel-level spatial invariance makes the model easier to overfit the density map noises. Please refer to our paper for more details. To solve these problems, inspired by the previous work, we try to replace the traditional convolution operation with multiple Gaussian kernels. The motivation behind this is to simulate the Gaussian-style density map generation throughout the whole feature learning process, rather than merely generating the final density map. To a certain level, this modification is equivalent to a relaxation of the pixel-level spatial invariance. After the pixel grid filters are revised with multiple Gaussian kernels, we can jump out of the over-strict pixel-level restrictions. More details are in our research paper.
At the post's request, researchers at Carnegie Mellon University used a crowd counting model to determine the number of people visible in videos and images. In this video, the analysis estimated there were at least 3,400 people. That number is likely an undercount due to the quality of available footage and obstructions like flags and trees. Around 118 of those present are officers, meaning they are outnumbered more than 28-1. The Post used a tool developed by researchers at Carnegie Mellon University to estimate the size and density of the mob at key moments. The results of that analysis were used to approximate rioters' locations for the 3D visualization. The analysis shows that by this time, at least 2,000 people have pushed past police lines on the east side of the Capitol and attempt to break in.
We stayed on that mid-terrace as long as we could safely. A decision was made by the United States Capitol Police to pull their personnel back inside the building at a point, leaving one of my flanks pretty weak.
At least 9,400 people are visible in footage taken during this time period, and outnumbered officers more than 58-1, according to an analysis by the Post and Carnegie Mellon University.
Thanks for watching. For more details, please read our research paper and poster.